Despite these caveats, their sheer number means they represent a vast, largely unexplored frontier for potential life, and we certainly can't rule them out.
That's a lot of potential homes. Which brings us to FLA, the fraction of stars with planetary systems. In 1961, this was pure speculation, with educated guesses ranging between zero point 0.2 and zero point 0.5.
Just an idea back then.
The idea that planets were common was just that, an idea. But oh, how that has changed.
It's been completely revolutionized. The launch of NASA's Kepler Space Telescope in 2009 was nothing short of a game changer. Kepler stared unflinchingly at a single patch of sky, patiently monitoring the brightness of over 150,000 stars.
Just watching for dips in light.
Looking for the telltale, almost imperceptible dimming caused by a planet transiting or passing in front of its star.
And the data, when it poured in, revealed a truly staggering truth. There are more planets than stars in the Milky Way galaxy.
More planets than stars.
Yeah.
Still amazing.
I mean, just let that sink in for a moment. Every single star you look up at in the night sky is likely the center of its own bustling solar system.
This profound conclusion has been consistently reinforced by subsequent missions like TESS and other detection methods, such as gravitational microlensing, which don't rely on transits. As of August 2025, the NASA Exoplanet Archive lists nearly 6,000 confirmed exoplanets, with thousands more candidates awaiting confirmation.
So the consensus now.
The scientific consensus is now absolutely clear. Planets are not the exception, they are emphatically the rule. Current research effectively pushes the value of FP to nearly 1.
FT is basically 1.
Okay.
And now, it's worth acknowledging that our current detection methods, like the transit method used by Kepler, tend to favor large planets in tight, short-period orbits.
That's true, there's a bias.
This means our current census is undoubtedly incomplete, and smaller, Earth-sized planets in wider, more Earth-like orbits are much harder to detect. We're biased towards the easy finds.
That's true. But even with that observational bias, the sheer volume of detections provides overwhelming and undeniable evidence that planetary systems are a standard, inherent feature of star formation. The value of Cree is confidently understood to be very, very close to unity. It's a foundational certainty in the Drake equation now.
Which brings us to the number of habitable planets per system. This is where we start asking if these incredibly abundant planets are actually suitable for life, not just if they exist.
Right, the potential homes.
The traditional starting point for this assessment is the Goldilocks zone, or more formally, the circumstellar habitable zone.
Exactly. This is the calculated range of orbital distances from a star where a planet's surface temperature could allow liquid water to exist stably.
Liquid water being key.
Crucial. But it's not fixed. The size and location of this zone depend entirely on the host star's temperature and luminosity. Hotter stars have wider habitable zones located farther out, while cooler, dimmer stars like red dwarfs have very narrow zones located much closer in.
And the zone can move over time, too.
Yes, as a star ages and changes, its habitable zone can actually migrate, expanding or contracting over cosmic timescales.
Kepler, once again, was specifically designed to help us understand, to find those elusive Earth-sized planets specifically within the habitable zones of sun-like stars.
And its results have been truly remarkable, changing our perception of galactic habitability.
What did it find?
Indeed, a landmark 2013 study analyzing Kepler data for 42,000 sun-like stars concluded that about 22%, roughly 1 in 5, of them harbor an Earth-sized planet orbiting within their habitable zone.
1 in 5, that's huge.
Then, in 2020, a NASA-led study combining Kepler's data with more precise stellar data from the Gaia mission refined this even further, concluding, and this is amazing, about half the stars similar in temperature to our Sun could have a rocky planet capable of supporting liquid water on its surface.
Half of sun-like stars might have a watery rock in the right place. Think about the scale of that.
It's staggering. This translates into occurrence rates for rocky, habitable zone planets, our new value, ranging from 0.37 to 0.60 under a conservative habitable zone definition, and even higher, 0.58 to 0.88 under an optimistic definition.
So even conservatively.
Even on the conservative side, this suggests our galaxy holds at least 300 million potentially habitable worlds, and the nearest one could be within just 20 light-years of Earth.
20 light years. That's practically our galactic backyard within shouting distance, cosmically speaking.
Absolutely. And we also have to stretch our imagination beyond the traditional Goldilocks zone. Some of the most compelling targets for life in our own solar system are the icy moons of gas giants, far from the sun's direct heat.
You mean like Europa and Enceladus?
Exactly. Jupiter's moon, Europa, and Saturn's moon, Enceladus, are believed to harbor vast liquid water oceans beneath their frozen shells. warmed not by sunlight, but by tidal heating from their massive parent planets.
Internal heating.
Right. These subsurface environments, rich in chemical energy, could potentially harbor life in ways we're just beginning to understand.
So if these subsurface ocean worlds are common throughout the galaxy, and there's no reason to think they wouldn't be, then even our current optimistic Kepler-derived values for Ni could be significant underestimates.
Could be way off, yeah. It completely expands the definition of habitable.
Okay, so summing up this section.
In essence, the astronomical data provides incredible clarity and even optimism for the first part of the Drake equation. The galaxy is far from barren. It's a fertile, dynamic nursery, consistently churning out stars and planetary systems in abundance, with potentially habitable worlds numbering not just in the millions, but potentially in the billions.
Billions of potential homes.
The big question, the great unknown, is no longer about the availability of real estate, but whether that real estate is actually occupied and what's living on it.
And this brings us to what many consider the great bottlenecks of the Drake equation. We're now pivoting sharply from the relatively firm ground of astronomy into the profound, often contentious uncertainties of biology.
The hard part?
These next two variables, flare and phi, tackle the very origin of life itself and the evolution of intelligence. This is where the debate gets truly fierce.
That's precisely right. Because unlike counting stars or exoplanets, when we discuss the emergence of life and intelligence, we're essentially working with a sample size of our own Earth.
Just us.
This single data point makes statistical inference incredibly difficult, if not impossible, and opens the door to intense scientific, philosophical, and even existential disagreement. It's the ultimate Anka 1 problem.
Let's start with Fellaway, the fraction of habitable planets where life actually develops. This asks a truly fundamental question. Given a world with all the right ingredients, liquid water, organic compounds, a stable energy source, what is the actual probability that life will spontaneously arise?
The mystery of abiogenesis.
The profound mystery of abiogenesis, the process by which life emerges from non-living matter.
For many of us, a foundational step in understanding abiogenesis was the iconic Miller-Urey experiment, conducted way back in 1953.
Heck yes, the sparks in the flask.
Exactly. Stanley Miller and Harold Urey constructed a closed system designed to simulate early Earth conditions. They had a flask of water to represent the primitive ocean, and then they introduced a mixture of gases thought to be prevalent in Earth's early reducing atmosphere, methane, ammonia, and hydrogen. Crucially, they then introduced electrical sparks to simulate lightning, providing energy.
And what happened after just 1 week was absolutely remarkable. The clear water in their setup had transformed into a murky, brownish-black primordial soup.
Soup from sparks.
Analysis of this soup revealed the presence of multiple organic molecules, including several amino acids, which, as many of us know, are the fundamental building blocks of proteins, the workhorses of life.
This experiment provided powerful early evidence that the complex molecules essential for life could spontaneously form from simple inorganic precursors under plausible early Earth conditions. It was a massive conceptual leap.
But it had limits, right?
It did. It also had significant limitations. Modern geoscientists now believe Earth's early atmosphere wasn't as strongly reducing. It was likely dominated by carbon dioxide and nitrogen, which yields far fewer organic molecules in similar experiments.
Okay.
And crucially, while Miller-Urey created simple building blocks, it didn't produce more complex structures like nucleotides, nor did it offer a clear pathway for these to assemble into self-replicating metabolizing cells, the true definition of life.
So it made ingredients, not the full recipe or the baker.
Something like that, yeah. So scientists looked beyond the atmospheric origins for alternatives, and a leading modern hypothesis centers on deep-sea hydrothermal vents.
The deep sea vents. Fascinating places.
They are. These are fissures in the seafloor where superheated, geothermally warmed water, incredibly rich in dissolved minerals and chemicals like hydrogen,